Okay, here we go again. So we're going to continuing with our work on energy. And so what I have here are two blocks that are on slants. Here are ramps. One at 60 degrees, the other at 30. The one at 60 weighs more than the one here at 40 pounds. Both of these ramps have friction, so 0.1 coefficient of static friction. And so here's what we want to do. It says right here, find the velocity of A when velocity of B, when B moves 2 feet up the ramp. So again, we're seeing velocity and distance. That is a clue to you having an energy problem. So, and we say that here. So we want to start knocking this one off. And so when you look at this, as this slides, okay, this path length is going to be important because there's going to be friction here. So friction's going to do work. So it's very important to know how far this goes and that goes. So we're told B is going to go 2 feet up the ramp right here. So if this goes up 2 feet, that says 2 feet of rope is going to pass down here. So what's going to happen? Well, 1 foot of that rope is going to land here. 1 foot's going to land here. So what that means is as this goes up 2 feet, this one's going to go down 1 foot. Okay? So here it says delta dB, there's a 2 foot shift. dA will have a 1 foot shift. All right, so we have that done. Now, let's look at a free body diagram of A and B, because we're going to, just so we can figure out all of our, the extent of all the motion and everything and get all of our angles right. So here we have, here's block A. So here's 60 pounds going straight down. And this is at 60 degrees. So if that's at 60, if we go up at 90, here's 30. So we could actually, if we wanted, just move that over here. And so you can picture 60 pounds going down right over here. All right. Now, we need to figure out this normal force. Okay, because the normal force will determine the friction force. That's why I call that NA over here. So, if we sum the forces along the normal, where I'm letting this direction be positive, okay, bring that up slightly. So, let's see here. So NA is going this way, and the friction is perpendicular, so don't have to worry about that. The tension is perpendicular, don't have to worry about that. So only thing we're left with is 60, okay, cosine of 60. So NA minus 60 cosine of 60 is 0. Solve for NA. That tells us the normal force here, 30 pounds. That means we have 30 times 0.1 is the friction force, and so we have everything we need for that. Same sort of idea here. Here we are at 30 degrees. There's the tension. Now here there's two tensions relative to A. We can see that here. Tension 1, say tension 2. One rope connection here. Here's at 30 degrees. Here's this coming down. And so when we set that up, 30, 90, 60, that puts 30 degrees in here. Okay, so going out this way positive, NB minus 40 cosine of 30, and that gives us what NB is. Okay, so we know the normal forces. I went going through all of this because it's really common for students to do a drawing just like this. So they'll show this piece, they'll show that, but they don't do the ramp. And they put this 30 degrees in, and they start getting confused what angles and everything is. So by just putting this ramp in, put the little 30, 60, 90 triangle in, it's really easy to see where everything fits. So the free body diagrams are very helpful. I recommend you use them. All right, so we're going to keep that. And let's see here. We should be able to have both sheets up. So slide that this way. Yeah, we got it all here. Okay, so here's our energy equation. So we have our initial state, which we have here, and then this is going to go up 2 feet. That's going to go down along the ramp 1 foot. And so we want to start building our equation. All right, so let's see. The thing starts from rest right here. So we'll go over here, and KE1, initial kinetic energy, it's 0. I'm going to call each of these to be in the respective ground position. This will go up to V2, this will go down to V2. All right, but I'm going to call PE1 0. It's a free choice. It's all right, I get to do that. Okay, now we're going to take a look at, let's fill that in here, 0 and 0. So now we're going to look at the non-conservative work. Okay, so let's see. We've got friction. So over here, its force of friction is 30. Remember, the normal force was 30 times 0.1, so that leaves us with 3. Okay. Then it's going down 1 foot, and it's going to be negative. The force of friction is this way, it moves that way. So we can just put it this way. Minus 30 for the normal force, 0.1 for the kinetic coefficient of friction, and 1 foot to go down. All right, negative. All right, now over here, friction's going the other way, it's moving that way. So we're going to have, due to friction, again negative. The normal force is 34.64, coefficient of friction 0.1. It's going up 2 feet. So we have that. All right. And if you multiply those out, you'd have minus 9.928. Okay. That would be foot-pounds. Or pound-feet, whichever one motivates you. Now, the tension. The tension here would also be doing work. And I want you to, let's just look what happens here. Over on A, it's moving this way, but the tension is going back. All right? So that's negative work. So that'll be 2 times the tension, whatever that is, and it's going down 1 foot. Over here, we have the tension, and it's moving in that way, so that'll be plus T, and it's going up 2 feet. Add them together. You get 0. In net, it does no work. So notice what we have here. This is internal work between here and there. That's internal to the system. That's why we had that discussion before. What is work about? Talking about external work. Okay? When you have internal work, it's going to cancel out. So what's happening is as much as one system helps another one along, the other one holds the other one back. It evens out. Okay? Internal work's got to be 0. Now, when you're doing a problem, you could have just looked at these and said that's internal and ignored them. And obviously you're going to get the same answer. If you start handling internal forces, that's okay too. They'll cancel out in the end. But you have to be consistent in how you handle them. Okay, the internals, they're going to cancel, but be careful. Make sure you handle them consistently. That's the only warning. Okay. So we have our the work due to friction. So now we have to look at the kinetic energy on the other side. And so that's going to be 1/2. So let's see. This one will be 60 divided by 32.2. So let's see. When this one goes up, its velocity, because of the pulley system here, this will go half as fast. So let's just eliminate a variable and call that VB over 2. That's what VA is. And then we have 1/2 for B, 40 over 32.2, and VB squared. Okay? Now, we have one more piece we've got to take a look at. And so let's see what we have here. That's going to be potential energy. Okay, so let's take a look at that one. So we're going to have this is dropping. We called this the 0 spot, so it's going to drop down a foot. So going down means it's going to be negative, so we have 60 pounds. Okay. The question is, so it's going down 1 foot along here. Okay, so the question is how far does it go down? That'd be 1, okay, sine of 60. So we have that there. By the same token, this is going up 2 feet, and we have that 30 degrees. How high up does it go? Okay, so the other side we have 40 pounds, and then 2 sine of 30 degrees. Okay, add all those up, the net is minus 11.96. Okay, so we can add all those things up, minus 9.928 plus all of that KE2, I'm not going to rewrite it, minus 11.96. Solve for VB, and we would get 1.54 feet per second going up the ramp. VA, which was what the question asked for. What is VA when it goes up 2 feet? Okay, half of that, 0.771 feet per second going that away. Next problem. Whoops. Too much paper. So here's our next one. So what we have here is, again, a pulley system. So whatever this does, this is going to do half of it, as the rope that's given up by this side is split between both of these halves. Okay, we have friction here. This is just an air, so no friction there. This is WA, weighs 3 pounds. This block hanging is 8. Starts from rest. Here's the coefficient of friction. Okay, and so here, find the distance B travels such that A gets to 5 feet per second. So again, distance, velocity, that's your clue. You're talking energy. Okay, so first thing we got to do is just very quickly deal with the effects of the pulley. So we'll just talk about that really quick. So if VA goes 5 feet per second, here, what does this one do? Or let's put it this way. Put an arrow here. Then this would be going 2.5 feet per second. Put a little equal sign in there. Or you could be saying VB equals 1/2 VA in magnitude. All right? Now, whatever change in distance this has, okay, let's just write it this way. 1/2 the change in A is equal to 1 times the change in B. So that allows us to relate these things together. All right. So let's see what we're starting with here. We're going to have friction here. So I started the free body diagram. I have 3 pounds. There's a normal force. This is obviously going to slide this way. So here's a tension. And we're going to have a friction coming back. That friction will be 0.3 times 3 pounds as a force. Okay? So let's see. We got that all lined up. So let's start in. We're starting from rest. KE equals 0. We'll say the initial positions are our zeros. PE1 is 0. So next thing is W1 to 2NC, so our non-conservative work. That's going to be, let's see, 0.3 times 3 times the distance that A moves. Okay, negative. That'll be the W1 to 2 non-conservative. Okay? T2 will be 1/2. Let's see, start with A. That'll be 3 over 32.2 times 5 squared, because it's going to get up to 5 feet per second, plus 1/2. Let's see, B is 8 pounds, so 8 on 32.2. So how fast is B going to be going? Okay, it's going to be going half as fast. As this gives up chord, it gets split between these two, so this goes half as fast. So we have 2.5 squared for this one. Okay, so let's see, if we add all that up, according to my notes, this is 1.941. Okay, now we have to deal with, so we've dealt with this one, we've dealt with this one, PE2. So V2, so let's see, this one A isn't changing in height, so there's nothing there. So I'll just add a 0 in here. And B is going down, so that'll be the weight, mg, and distance, b. Okay? Now, life would be so much easier if I only had one variable. So let's see, I can rewrite this if I wanted to as minus 8 dA over 2. Okay, because b will go half the distance a does, so that would make for minus 4 dA. So, pulling all this together, I have minus 0.9 dA. Oops. That's coming from up here. Equals 1.941 minus 4 dA. Solve. Get dA is what? 0.626 feet. Solve for b, which is just going to be half of that, 0.313 feet. All done. Now, we're going to do one more of these. One more problem. Okay, so for this one, what do we have? The same sort of pulley thing, so as rope is given up here, it's split between here and here. And we have this one block, so a 50, calling it a box here, so 50 kilogram box. All right. And let's see what the problem says. Initial spring tension is 60 newtons. Okay, let's just think about that for a moment. So 60 newtons. So that says that there's a 60 Newton force stretching this spring. Well, that would correspond to the spring constant, 300, times how far that's stretched. I'll call that D. So 60 equals 300D. It says the stretch in the spring is currently 0.2 meters. Okay. So if we go and take this over here, so if D is stretched by 0.2 meters, that says this thing's going to drop because of that. So you start, if this was unstretched, and so you had your hand under it, okay, and then you let it go a little bit, so that this stretched 0.2 meters, that says this would be stretched 0.1 meter. Down. Okay? So that'll be dropped. So in our initial position, we have this is stretched a bit, this is dropped a bit compared to the unstretched position. All right? And so so now we're asked, find the velocity of this box. So picture that you have your hand under this. So you've let it fall a little bit, but you haven't just let it go and go doing, 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 doing. Okay? So you have your hand under this. You've allowed a little bit of stretch in here. And now you drop your hand 0.2 meters, and so you're going to let it go. Fall that far. And so what's the velocity after it's fallen that far? Okay? And then we're going to do it again and say, how far will the box fall to the first bounce? So if you just let it free fall, there will be some point where it will go, the velocity will hit 0, and then it will start coming back up again. Okay? So we're going to do this twice. So here's the first case where we're going to let it drop 0.2 meters. So if this drops 0.2 meters, because it means you have 0.2 meters here more and 0.2 meters here more of rope, that says up here we're letting this go an additional 0.4 meters. All right? So let's apply that. We're starting from rest. So KE1 is 0. I'm going to let this position be the 0 position. So it has fallen 0.1 meters already due to the stretch, but I'm going to call that spot my 0 position. Okay? So on PE, that says I'd have a 0 relative to that part, but I have energy in here. We let that stretch already. So we've got to describe all of the energy at the start. No problem. So we had, this was a 0. This is due to gravity. Now the spring, we have plus 1/2, 300 newtons per meter, and we already have a stretch of 0.2. So we squared that, 1/2 kx squared. That side's done. KE2. Okay. We let this fall 0.2 meters. The box will have a velocity. So let's see, 1/2. We've got 50 kilograms. And we don't know how fast that's going, so we'll just call that v squared. All right. We know it's going to fall 0.2 meters. So 50 kilograms, 9.81, 0.2, and let's put a minus sign in there. So that's negative potential energy happening. Okay, and now we have, so we've hit, this has two terms, the gravity term and the spring term. So let's think what happens now. That spring, 1/2 times the spring constant, it was already stretched 0.2, but if this falls 0.2, it'll stretch 0.4 more. So that's 0.2 plus 0.4 squared. Okay? Looking at this, we have one variable, solve for v. We come up with velocity is 1.42 meters per second. And I'll let you take a look at that for a moment. Okay? So that's part 1. Part 2, oh, here's part 1. Part 2, how far will the box fall to the first bounce? Okay, well, let's do it all over again. KE1, and I'm starting from the original position, as it were, was 0. Let's just write the whole thing out. KE1 plus PE1 plus W1 to 2 NC equals KE. Let's call this state 3, the first bounce, not to confuse them. So I had a 0 there. Relative to gravity, I had another 0. Then I had the stretch of the spring when we started. So 1 plus 1/2 300.2 squared. Okay. There was no, if we should just probably should have made a point of this more last time. No friction, no motors, so that term's 0. Okay. Now, when it hits the first bounce, well, that'll give us 0 for the kinetic energy. So I'll just bring that in there. And so the question is how far is it going to fall? We don't know. So let's see. So for PE for gravity, it'll be negative 50 kilograms, 9.81, and we'll just say it's going to fall some distance y. I don't know what that is, but we're going to find out. Plus, okay, the spring is going to stretch as it falls, so 1/2 300. It had already stretched 0.2, and if it falls y, it's plus 2y. So 0.2 plus 2y quantity squared. Okay, we're all set. Solve for y. I'll let you do the math, but if you go through it, here's what you're going to get. Y equals 0.6175 meters. And there we have it. All right, I have another problem for you to do. See you soon.